Hello everyone, welcome to our Capstone presentation on the production of PLA from potato peel waste. Quick agenda, we're going to go through the intro, then the process and P&ID, business plan, safety analysis, conclusion, and finally any questions.
Just for a team introduction, I'm Emma. I'm a fourth-year senior. Both of my co-ops were in chemistry co-ops, and I'll be working at National Grid after graduation.
And I'm Jake. I did my co-ops in biochemistry and Merck and neon therapeutics, and I'll be pursuing my PhD at Harvard.
I'm Mina, and I'm also a fourth-year senior. I did my first co-op at Adaptive Surface Technologies as a polymer scientist, and my second co-op at C2 Sense as a manufacturing engineer.
I'm Zakrzewski. I'm a fourth-year senior. I did my first co-op as an engineer at UGI Energy Services, and I did my second co-op at VS Separations as an engineer as well.
Hi, I'm Josh, and I'm a fifth-year senior, and both my co-ops are also chemistry co-ops. So, just as an introduction, traditional plastics are fossil fuel-based polymers which are used in everyday life, but due to lack of recycling and poor disposal, there are growing environmental concerns. Some examples of these polymers are polyethylene and polypropylene, which are primarily used in packaging, polystyrene, mostly used in cutlery, polyethylene terephthalate, which is mostly used in clothing, and these have a long degradation time and essentially do not biodegrade. So, an alternative are bioplastics, which are plant-based polymers. They are made from renewable resources, and they are a renewable alternative, and they have much faster biodegradable time, as fast as 6 months in the right environment. Basically, this project incorporates our team's interests of chemical analysis, materials, and biotechnology. So some more background. Every year, 300 million tons of plastics are produced. Half of that are single-use, and a large portion of this ends up in the environment, both in the landfills and the ocean. Also, another downside is chemical toxins are released during the production of these plastics. But it's important to know, while these problems exist, the plastic industry has become extremely successful and is used in everyday life. Thus, we cannot simply replace it, but we must find innovative solutions to reduce these problems. And that brings us to our bioplastics. As stated before, they are from renewable sources containing cellulose, like corn, bagasse, and spent coffee grounds. Specifically, we're looking at polylactic acid, or PLA, and this performs similarly to polystyrene, polypropylene, and the market for it is expected to grow substantially over the upcoming years. So, the production for PLA is the same after you extract sugars from the raw material. Thus, to improve the overall process, we looked at the different raw materials. Starting with corn. Corn was priced about 6 cents per pound. In 2014, NatureWorks was the largest manufacturer of PLA at producing about 150,000 metric tons, and they used corn as their raw material. Unfortunately, it requires a large amount of land and resources, therefore it's not environmentally friendly. So we looked at another source, bagasse, which is the dry pulp from sugarcane after sugar extraction, and this is priced about 7 cents per pound. But the problem with this is that the market is expected to grow substantially over the upcoming years, therefore the price will also increase, not making it very viable for us. Finally, we looked at spent coffee grounds, which are the shells of coffee beans after the brewing process. This was very promising for us as it was a waste product, thus zero cost for acquiring it. But unfortunately, after doing our material balances, we found that there wasn't enough to supply our production rate, not even in the world. So, thus led us to potato peel waste, or PPW, and this comes from potato chip processing plants, or French fries, as shown here. And potatoes itself, 15% of it is starch on a mass basis. Estimated about 400 million metric tons of potatoes produced every year globally. Doing some calculations and conversions from literature, that turns out to be 18.6 million metric tons of potato peel waste on a similar scale. Potato peel waste is typically used as animal feed and fertilizer. So our problem statement here, Biogem seeks to create 50,000 metric tons of PLA resin from potato peel waste as a viable alternative to fossil fuel-based plastics such as polyethylene, polypropylene, and polystyrene. This resin will be marketed towards packaging manufacturers as a more economical and sustainable raw polymer resin for use as a precursor to single-use consumable plastic products. To sum this up, essentially, bioplastics exist today, but they struggle because they're not cost competitive enough. Biogems decided to use potato peel waste as a cheap raw material with similar chemical biodegradable composition as the end product. Ultimately, our novel process and production goal will also be competitive in both the bioplastic and traditional plastic market.
So how do we get PLA resin from potato peel waste? There's a number of steps that go into this. We'd like to highlight that to make lactic acid, you can make it synthetically or bacterially. We decided to use bacterial fermentation because it leads to a more stable end polymer. We also have 2 steps between creating lactic acid and polymerizing our lactic acid. This includes what's called a pre-polymer, which is basically a low molecular weight chain of lactic acid molecules. We also make a lactide intermediate, which further improves the quality of the high molecular weight PLA that we're creating in the end. So how do we actually make this in an industrial process? We have a simplified block flow diagram here that walks through the different steps. First, we boil the potato peel waste to extract the starch and cellulose molecules. Then these go into an enzymatic reactor with enzymes to create sugars. The sugars are then fermented with bacteria to create the lactic acid. The lactic acid is purified through several steps, including filtration of the extra biomass in distillation and making the pre-polymer. And then there's the lactide reaction, and finally polymerization, crystallization, and drying. So how do we get 50,000 metric tons of PLA a year? We had to back calculate to figure out how much potato peel waste we wanted to start with. We did this through research of the efficiency of each step of our process, and we found that we need about 1.1 million metric tons of potato peel waste a year to keep up with our production. But luckily, as Josh mentioned, there's more than enough potato peel waste in the world produced each year to keep up with this. Due to the low efficiency of boiling, we'll also create about 900,000 metric tons of biomass each year, but we do have plans to possibly incorporate this back into our system in the future. And we use just under 300,000 tons of processed water in our system. This is mostly used in the boiling process. So the end product, PLA resin polymer is our end product, and it has a smooth surface and is a stiff polymer at room temperature. It has a melting point of around 170 to 200 degrees Celsius, which is in line with other plastics such as polystyrene and is manipulatable.
So onto the piping and instrumentation diagrams, they were developed by a team from multiple patents, literature, and textbooks, but we would like to note it's novel to us and was 100% drawn by us. So we broke it, there's 13 unit ops, so we broke it up into 4 whole pages for you guys to digest: lactic acid production, lactic acid separation, polymerization, and then PLA purifying and drying. So this is our first PNID, which is going to depict our lactic acid production. And what we'd like to draw your attention to here is our storage tanks. So after the cellulose goes through our enzymatic reactor and our fermenter, it will go into our storage tanks where we'll sit for about 3 days. That's kind of a new thing in our process. And then after this area, it will continue on to our lactic acid separation. Now, what we'd like to draw your attention to on this PNID are our steam lines. So our steam lines are going to be set to the highest reactor jacketing temperature that's needed in our facility. Then every reactor in the facility is equipped with process control that can vary how much of that steam is let into that reactor jacketing to control the temperature that's in that reactor. And that is continued onto the outlet where it's then recycled back into our stream. The same principle is also used for our cooling lines throughout the system. On our next PNID is our polymerization steps, which includes both our distillation columns. And what we'd like to talk about here are the inlet streams. So on every inlet, on most reactors, there is an inlet stream where we're adding chemicals in there. And there is process control there, so there is a pneumatic valve and also a flow transmitter. There's many transmitters throughout our facility, and those are actually sent to a control room where an operator is watching, and then he'll relay that back to a pneumatic valve to open and close that valve. And the reason we have this is because such a new and novel process is going to need operator supervision for the most part in the beginning of our process. But even with operator supervision, we do need safety implementation. So any reactor or any area there might be a pressure overrun, we have PRV, pressure relief valves equipped that are set to 14.7 psig, which are well below any other tolerances that our tanks need. So safer the better there. And then for our last PNID is our PLA purifying and drying. What we'd like to draw your attention to on this slide are our IRDs. So after the PLA resin has finished the whole process, it needs to go into our IRDs, which are infrared dryers, which is essentially a combination of a crystallizer and a dryer. Once going through the IRDs, it will dry, go onto a conveyor belt, gum out. They get pulled by a vacuum drum and sent into our hopper cars, where it'll be sent right on the railroad to direct distribution. So the bioplastics market as a whole in 2018 globally produced 2.11 million metric tons. In the United States last year, it was 337,000 metric tons. Now, there is a 20 to 30% year-to-year growth in this rate, so that means there's more than enough space, and it's well and adequate to support Biogem's entry into this market. And as well, there's about 10.3 of that bioplastics market globally is PLA. So once bioplastics enter this market, we really hope to bring up that percentage of PLA in the market. Now, the established bioplastic producers in the market, as some of us talked about, are going to be NatureWorks, Toray, and BASF AG. They do have about 50% of the market share, but again, with that 20 to 30% year-to-year growth, there's more than enough space for Biogem to enter the market. And one factor that we're really happy about is that 25% of customers are willing to pay an extra cost for an environmentally friendly product to have that package in. So our marketing strategy, so Biogems will be established as a corporation and will also be marketed to distributors as the first part of the supply chain. The reason we're doing this is this will help us gain traction within the market and also trust within the market. Later on down the road, we might do something else on our distribution platform, but in the beginning, we're going to be using resin distributors to get our product out there. And companies can also improve their brand image by using this product. More and more today, consumers like to use products that are environmentally friendly, and if there's one option that's environmentally friendly and one that's not, they're going to more than likely yield to that environmentally friendly product. And then last, we'd like to note the largest traditional plastic producers are ExxonMobil and Chevron. The reason we're bringing this into light is for our two-tier marketing strategy. So this is our current marketing strategy where we go to our bioplastic buyers. But then there's also the people who use ExxonMobil and Chevron. Those are the commodity plastic buyers. So in the beginning, we're only going to bioplastic buyers, but as time goes on, those bioplastic buyers, we're still going to give them the competitive price level know and love. And the benefit of our plastic is that it doesn't require any extra land. We're using a waste material and so forth. But to the commodity plastic buyers, we're going to market our product under a different name with a different price point to help us get in there. That's more competitive with the conventional plastics that are marketed by Chevron and ExxonMobil and companies such as like that. And the reason they'll want to do this as well is, yes, there is a little bit extra cost, but in the end, it's great for their image. So our supply chain. So we're going to be based in Eagle, Idaho. The reason for being based in Eagle, Idaho is that where the majority of potato processing facilities are in the United States, and then they'll be transported down via 477 hopper cars a year down to Dallas, Texas. The reason we're going to Dallas, Texas, that's kind of the break of bulk point for plastics in the United States, so all plastics are kind of sent there, especially the ones produced in the Gulf Coast. So because we are in Eagle, Idaho, we do have that cost disadvantage from coming all the way down, but because of our raw material cost being essentially free, we can actually negate that cost. We have done calculations so that we can still make a fair share of profit, which Mina will talk about later. Our plastic will also be shipped using a freight on board basis. So once that product gets to Dallas, it will be marketed at the same price, and that essentially the shipping cost from that point to any of the manufacturers is going to be the same across the board for our plastic, or our plastic from NatureWorks, or our plastic from ExxonMobil, and that's really going to help show our cost competitiveness. And once that product's in Dallas, we're going to be giving it to, as I said before, resin distributors such as Ashland or M. Holland, who will then send it to plasticizers who will figure out the chemistry of that product, who will then send it to the thermoformers who will put that into the bottle, and then send it to a filling company such as Coca-Cola, and then they will send it to a grocery store such as Wegmans and so forth.
All right. Moving on to the economics of our plant. I would like to let you guys know that we used a class 4 estimate using the chemical engineering design textbook to come up with our equipment costs. And as you can see in the pie chart, our storage tanks, because there are 8 of them, is our most expensive cost, followed by our boilers and our reactors. Oh, sorry. So our total capital cost comes out to be around $12.2 million. And to be able to calculate our total fixed capital cost, we need to be able to know our ISBL, which is our inside battery limits, our outside battery limits, our engineering and contingency costs. So our inside battery limit costs are actually the cost of purchasing all the equipment and piping together, and our outside battery limit costs is the cost of all the utilities and all the extra equipment needed to construct our plant. So our total fixed capital investment comes out to be $72.7 million. So our yearly production costs can be separated into 2, our fixed costs and our variable costs. Our fixed costs, as you can see, are listed on the left, total about $5 million. Our variable costs, is important to note, consist of transportation of potato peel waste to our plant, waste disposal costs, utilities costs, consumables, packaging, and distribution costs. And it's also important to note that our raw material cost is $0 because we are using free potato peel waste. So our variable costs total $30 million, and in combination, our cash cost of production totals $35 million. Our annual profit and revenue can be calculated using our selling price of 90 cents per pound. So our revenue comes out to be $99.2 million, and our cash cost of production, as I stated before, is $35 million. So this results in our gross margin of $87.4 million and our gross profit of $64.2 million. After taxes, our net profit comes out to $51 million. So when we compare our raw material to all the other raw materials that we could have used, such as bagasse and corn, we see that if we were to use bagasse, we'd have to purchase it at 7 cents a pound, which would give us a purchasing cost of $48 million that we didn't have before if we use potato peel waste. This results in a net profit of $12.7 million, which is a great reduction in our net profit, as you can see, from $51 million. Similarly, if we were to use corn as our raw material, we would have to purchase it at $6 per pound, resulting in a purchasing cost of $49 million and a net profit of $11.9 million. So our plant economics, we constructed a discounted cash flow analysis, and we were able to construct this graph of net present value against time. As you can see, we will be running our plant for 30 years, which is in line with other production plants around what we're doing. Also, our break-even point, as you can see around here, is 2 years, and our internal rate of return comes out to be 45%, which shows that we are very profitable for investors. Now, in comparison, when we think about the two-tier marketing strategy that we explained to you before, if we were to go into the commodity plastics market, we would be selling at 70 cents per pound, and this would give us a break-even point of 3 years, and this is not much of an increase, so this is great. And also, our internal rate of return turns out to be 42%, which is not a great decrease from 45%, and we're still very profitable, and we are still very attractive to investors. Our energy efficiency and optimization was thought out throughout our planning of this project. We came out with two possible ways that we could optimize our energy efficiency. One being by incorporating a steam turbine over our boilers. However, the boilers only would generate about 3.1 kilowatt hours of energy, and this would only save us about $1,800 per year, which is actually less than 1% of our total utilities cost today. So this isn't really a feasible option for us to invest our time in. The other possibility that we thought of is burning biomass to generate electricity. However, since our biomass does contain sulfuric acid, we thought that this would be a dangerous option, and we would have to put more thought into purifying the sulfuric acid out, and Jake will talk about this more in our future slides.
So safety will be a priority at Biogems, and so we did a series of HAZOP analysis and layers of protection analysis. So from this, we found our main hazards were associated with the fact that our facility is operating at such high temperatures. All of our equipment is over 80 degrees Celsius, and some of our reactors are even over 200 degrees Celsius. So to take this into account, this is definitely one of the hazards that we have to mitigate. We also have 5 reactors, which leads to the possibility of runaway reactions with our exothermic reactions or unintended byproducts. So for risk mitigation, we took into account inherently safer design considerations. One of the considerations we put into place were using smaller batch sizes. So as Sam talked about, we have the different storage tanks for fermentation. This reduces our overall batch size in each piece of equipment, making it an inherently safer design. We also will use water to heat and cool our process whenever possible, and we'll clearly label all of our valves, lines, and vessels for operators and engineers to easily identify what's going through each line. We also want to incorporate ARC testing, or accelerated rate calorimetry testing, to characterize our exothermic reactions. This lets us know if and when there are runaway reactions possible, so we can further mitigate this risk. We'll also ground and bond all of our equipment. Since there are reactions and a lot of material going through piping, there's always the opportunity for static electricity buildup. So by grounding and bonding our equipment, we'll reduce the possibility of there being an ignition spark. We'll also always have routine maintenance, PPE required, and extensive alarm and sprinkler systems on our equipment, as well as a lockout tagout protocol during maintenance, and dust control, because there is the possibility of creating condensed flammable dust in our facility, so we'll make sure to take this into account.
All right, so next up we got our proof of concept portion of this report, so our experimentation side of things. So what we did was we want to do 2 things. One, we want to prove that we can make lactic acid, and 2, we want to find a yield. We want to prove that we can make lactic acid because that was a novel portion of our report. It's well known going from lactic acid to polylactic acid at that polymerization step. And also, we don't have the means to do that at Northeastern, so we focused on the lactic acid side of our report. So we did that, and we also defined a yield because we wanted to see how many mgs per mil of lactic acid we were able to achieve in our first shot in experimentation. In our report, we used published findings from research journals because that would be more accurate for a scale-up process. But so we designed our experiment. Basically, we take potatoes, boil them, add some water, we make this potato peel mash mixture. You add some enzymes to it to break down the starch and cellulose. Then you adjust the pH with sulfuric acid, and then you get this bottom left image there. That's our before. And then to the right, our after. It's after 3 days of fermentation using lactobacillus. So you get a slight color change there. And here's Josh and I looking pretty in Professor Lustig's lab. Him and Professor Lee were happy enough to help us out and give us their lab space. And then we did the LCMS, or liquid chromatography mass spectrometry portion of the experiment in the Barnett Institute with Sue Abatiello. So we'll go into that a little bit. And if you're not an expert in LCMS, that's okay, I'm here for you. I got a crash course in LCMS. Basically, we have a graph here, and what LCMS does is it both separates a complex mixture. In this case, we're separating based on polarity, and also will give you the mass of each of the components that comes out. So on the x-axis, you have time. It separates the mixture over time, and the y-axis is absorbance, or basically the amount of the compound. So we want to separate that mixture from the slide before, the fermented potato peel waste. So we have this complex mixture of a bunch of different acids, so we want to find our lactic acid. Did we make that? Well, big red arrow says yes, we did make it, or we think so at least. This first graph is what we think is lactic acid, and then the subsequent graphs below it are basically cleaned up versions of that initial graph, ignoring everything else that's not a very specific mass of 89.0246, which is not actually the mass of lactic acid. That would be 90.08, but an LCMS subtracts the weight of one proton in the way we ran it, so you get the weight of 89.0247, which is basically exactly what we got, so it's a very good sign. We think we got lactic acid. How can we make really sure though? Well, another thing LCMS does, it fragments compounds, so sometimes a molecule will break into 2 or more parts, so in this case lactic acid will break into 2 parts, so it'll lose the mass of CO2, so it'll go from 89.02 about, which is that green line, to 43.02. So because we had both those masses here, that's another really good sign we got lactic acid, because another similar compound like formic acid with a very close molecular weight will not fragment in such a way. So another good sign, pretty sure we have lactic acid. How do we really make sure though? Well, we can run lactic acid on the column. So we bought some Beauty lactic acid from Amazon, and we ran this on our LCMS column. And 2 things we want to look for. One, did it come out at the same time? Because I mean, it would be the same polarity as before. So yes, it did, 6.67 minutes, that's a good sign. And 2, does it have the same exact parent and fragment mass? And yes, it does. It has that parent mass of 89.0246 and the fragmented mass of 43.02. So we got lactic acid definitely. So, but we needed a negative control for the study. So what if our fermentation did nothing and made no extra lactic acid? So we compared that to an unfermented sample of our potato peel mash. And ideally, we'd have little to no lactic acid, and what we found, interestingly, was there is lactic acid in our potato peel mash mixture. So we ran it on the column, it comes out at the same time, it has the same mass, and if you look at the peak area, it's 41,000, very low compared to our previous peak areas, which basically means the amount of lactic acid, and if you do the math, I'll explain in the next slide, but it's about 0.4 mg per mil concentration, so very, very low amounts of lactic acid, and we think this may be due to endogenous lactobacillus bacteria in our sample from the air or something, or possibly lactic acid in the potatoes themselves, although we would need some further experimentation to say for sure. So next up, our yield I talked about before. We do something called the standard addition method, which I won't get super into, but basically we're adding a set amount of lactic acid in microliters here 3 times, and then you get a direct correlation with the increase in absorbance, and then you can back calculate and find out how much lactic acid is in your original sample. So we back calculated, and then we found we get about 13 mg per mil of lactic acid in our sample, which you don't really know if that's good or bad. But in our research findings, we found anywhere from the single digits of lactic acid in mg per mil to about 100, and we used about 100 in our report because that was a well-published finding. So not bad for a first shot of our experiment. So we made lactic acid, good work there. But what can we do next for maybe the next Capstone team? Well, there's a few things. We talked before about possibly burning our biomass. We have 900,000 metric tons of it. So we could burn that to produce power, and this would produce a lot of power. However, we need to install a flue gas scrubber to scrub out the sulfuric acid compounds from the potato peel waste. We could also incorporate countercurrent heat exchangers in our hot and cool streams, make our process more efficient. We could use various other food waste sources like those spent coffee grounds, increase the capacity of our plant, produce more PLA per year, making us a competitor with companies like NatureWorks. We could also compete with NatureWorks because they produce their own plastic water bottles, and we could do the same, produce our own consumer products in-house. We could also make production improvements on the lactic acid side of things, so there's a ton we could do there. We could use different strains of lactobacillus. We could use different concentrations of enzymes, more time boiling, more water, et cetera, et cetera. We talked before about the two-tier marketing strategy. So first, we're marketing directly towards the bioplastics market, but we can also market towards the traditional plastics industry as well as the bioplastics market at those 2 price points, which would be great for our company. And of course, there are other atypical uses of PLA that aren't often used in the bioplastic industry. For example, textiles, hygiene products, filtration, separation, and medical devices. So a lot there we could look into. So in conclusion, we are able to produce 50,000 metric tons per year of polylactic acid. We are pricing this polylactic acid at 90 cents per pound, which undercuts the current PLA cost by 5 cents per pound. This gives us an IRR of 45% over that 30-year lifespan, leaving us a net profit of $51 million per year, which is not bad. And with that money, and with this yearly production of PLA, we are able to lower the plastic impact on the world today and succeed in our vision at Biogems of making a greener world for all of us. So I want to give some special thanks to a few people. One, of course, Professor Pfluger for all her help and assistance in this report. All the people who helped us in the lab, Professor Lustig, Lee, and Sue Abatiello in the LCMS Institute. Julianne Burke, which is Emma's sister. She made our Biogems logo for us, which was great. And then, of course, we got Paul with all of his assistants coming up to meet us, talking about where we fit in the bioplastics market compared to the traditional market. He helped us out a ton, and many thanks to him. We have gotten you a gift like no other. There you go, Paul. Thank you so much.
All right. And this is PLA.
And that, of course, it's PLA. It's our first sample.
Thank you.
So yeah, thank you guys so much for listening. And we'd love to take some questions. So go ahead.
How did you come up with the process?
So we looked into many different encyclopedias, chemical encyclopedias, actually in the library. We were sitting on the floor reading them. Then there's quite a few different research papers getting from cellulose and starches or sugars to lactic acid, and then different papers getting from lactic acid to polylactic acid. So it was a combination of all those different sources.
What did you assume for the cost of disposing of your waste?
So we have waste disposal costs somewhere.
Yeah.
You want to talk about that?
Yeah, it's in the backup slides.
Well,
So our numbers were basically estimated using the chemical engineering design textbook that we were given in Capstone 1, and the cost of disposing of waste was taken as a percentage of total variable costs. I can't remember the exact percentage that it is, but that's how we estimated it.
Oh, here.
Yeah.
Waste disposal.
4.7.
Yeah.
Yeah, $4.7 million.
Yeah.
Thank you.
Could we go real quick to the LCMS slides?
Oh yeah.
On your sample that you ran, on the middle graph, it looked like there was. Yep.
This one? Yeah.
Yeah, there was that small.
Yeah, that's interesting. I'm not sure why that peak came up exactly, because this is supposed to separate. It's like MS1 and then MS2. It's you separate just by the mass you're looking for. So interestingly, we got that small peak there, but at a much different polarity than lactic acid. So it wouldn't be lactic acid, but I think it may be formic acid, which is a very close in molecular weight to 89.0246. I think it's 88.99. So that first screening may have excluded everything but formic acid, and then further screening of more exact at exactly that molecular weight excluded that formic acid and just left our lactic acid. I think at least. Does that answer your question?
would formic acid cause issues down the line if you guys generated a large amount of it in your process?
We don't think so. It should separate out with our 2 distillation columns, so we should be able to remove that, and we have the waste disposal cost improvements.
I know you guys mentioned that obviously a big advantage to bioplastics is that they will degrade in the shorter lifespan than traditional plastics. What do you estimate your product would be?
Yeah, so there's been a few studies done on polylactic acid and their degradation times. So it's both biodegradable and compostable. So there are the best way to compost PLA is through composting. So there's commercial composting facilities that it can degrade in, I think, 90 days or less. But that's a commercial facility. You can compost PLA yourself in a few months, and it'll degrade. But that's not, most likely it's going to end up in the oceans or in a landfill or something like that. And less than a year is what most of the things I read was it will degrade by UV light and bacterial means.
I'll piggyback on that. So then, if you're selling this PLA to, I know you're going to be using it to actually just sell it as a resin to somewhere else. What would they use it for?
A lot of things. Our main suggestion for use of it is to create consumer goods. Since it's so similar to polystyrene is used for food packaging or cutlery that you just throw out after one use. So it could very easily be used for that. It could also be used for just bottling, all of those one-time bottles that you get full of, like Sam mentioned, Coca-Cola, and then just throw out. Could be used for something like that. Creating bottles would require additional thought into how to structure the bottle, which could possibly be a whole other Capstone project. That was one of our initial ideas.
Something also cool is PLA is one of the only plastics used in medicine because they use it as screws for after surgery, and the interesting thing is it'll degrade in your body as well. So as the plastic degrades in your body, it will also heal the wound, like bone will grow in. So PLA is the only one used in medicine. That's why you can sell it way upcharge to in medicine. So that's kind of cool.
Is the bacteria used in the fermentation process reusable, or is that like one time then you have to use new bacteria?
So it is reusable. You can ideally how I'd envision it would be you would culture lactobacillus bacteria separately and then kind of seed in your bacteria with each batch. Because if you're using the same strain of bacteria over and over again, eventually it'll mutate and you possibly won't be as efficient, possibly make toxic byproducts, stuff like that. So you'll probably have many stocks on the side where you'll use the same exact strain of lactobacillus, so you don't get any batch-to-batch differences.
What do you see as the major technical risks in developing this process, and what stages do you see yourself going through to get to the commercial plant?
Probably making sure that the distillation columns are functioning properly. So we did use a computer program called SuperChems to graph out the TXY diagrams and see how many trays we would need, but then actually in practice, making sure that that's correct and we are distilling off all of the impurities that we want. So probably the purifying steps. But
So you envision building the commercial plant at this scale before you did anything else from what you've done?
So we'd probably use, we were going to use aspen, but it was a struggle to use polymers in aspen. But we'd probably use further analysis to make sure that our plant is exactly up to scale before we build it, yeah. There'd be further development.
You wouldn't build a pilot plant?
Good.
You mean like a small version scale of it?
Yeah.
Yeah. No, that's definitely, so what we were presenting to you today was just kind of where we see ourselves being with that full scale, but yeah, down the road, definitely for like another Capstone project, doing a pilot plant, and then kind of meeting with other engineering contractors and being like, oh, how would we get this done? And that exactly, absolutely, go from, small scale, which Jake was doing in the lab, and kind of scaling that up, kind of automating that, and having a little small scale pilot plant, like you're saying, absolutely, then kind of just growing that up, getting our proof of concept, getting that venture capital in, to where we can prove that, this is an economical, this is a profitable process, and we can do it.
Thank you.
This is me speaking from complete ignorance words about how bacteria work, but how do you keep them from mutating before you add them to the system? Like you have multiple stocks.
So yeah, so how it works in the labs, I do my co-ops biochemistry labs. So I'll give an example. So they use there's a movie I think called Heck, or maybe something else, but there's a movie about this Henrietta Lacks and how her cells were taken from a tumor in her body, and now they're used globally around the world for experimentation, and without her consent. You should watch the movie. But
I've read the book.
okay, yeah, exactly. So you'll have like one stock of your bacteria that you can make a bunch of, and then you can freeze samples, basically, of very concentrated samples of cells, and then those are, you can consider them all the same, or nearly the same. And then when you're growing up the cells, usually you want to throw them out after a specific amount of multiplication, so like 30 life cycles of the bacteria, then you would consider them at risk of mutating and creating something else you wouldn't want. So you wouldn't want, and then you would throw away your bacteria. So we could reuse it a few batches depending on how long, depending on how many times they mutate, but then you would just take your frozen stock of like your initial sample of lactobacillus.
If you were to implement like more types of food waste, would you be able to use those in conjunction with your potato peel waste, or would you have to rethink like your initial? Does it take a different amount of like water and stuff like that to process like coffee?
Good question.
Yeah, it could possibly take a different amount of water, but we back calculated the water based on a potato peel waste into lactic acid paper, and how much, at one point it was like 88% lactic acid in the solution, so we back calculated how much water we would need for boiling. So we'd probably take a similar route if we were going to use coffee beans in conjunction with this. But the material, or the equipment, you still boil and then use an enzymatic reactor and fermenter, so we wouldn't need all new equipment.
Yeah, everything's the same up until like getting the sugars. So in this case, for potatoes, we extract the starch, break down the starch into sugars, and then from there, everything's the same. So you could start from bagasse, spent coffee grounds, corn. As long as you get to that sugar step, everything's the same. So there are a few differences between, and that's another reason why we chose potatoes, because it was the best of the options.
So you may have mentioned it, but have you accounted for, so obviously you're starting with biomass, have you accounted for how the cost of that might change in times of drought or poor production years?
No, we haven't.
But there is about 18 million metric tons of potato peel waste made every year, and we're only going to be using a fraction of that at 1 million tons. So hopefully it wouldn't fluctuate that much. We do need potatoes always, but that's a good point.
For your projections, you just assumed that it would remain constant through the
Yeah, because
your plan.
well, as we go down the road, like we'll work on IP and things like that to try to reinforce our stake. And then if someone's trying to produce the same material from cellulose or potato peel waste, we're really going to cut them out. And also, there is just so much right now of potato peel waste, and really just be using for like feedstock and things like that. So really, they're just trying to get rid of it the best way they can. So down the road, I don't really believe there'll be a wonderful use of potato peels like that, but if there does, we can definitely implement our facility to use other waste materials as well. We, as Sarah asked, we can use like coffee grounds and things like that. We can change our system to use any materials that adapt to the market.
Can I piggyback off that and say, do you know what they use or what they do with the potato peels now?
Yeah, so we mentioned
Feedstock.
Or not feedstock, fertilizer and I think your livestock feed.
Livestock.
Yeah.
Oh,
livestock feed and
livestock
fertilizer.
feed, yes. Not
Right.
feedstock.
Nice.
That's a common use of the site.
Do they sell it?
No, zero waste
Because they're not
waste product. So otherwise, they'd have to pay to truck it away.
Totally.
So they just give it to. There's nearby livestock farms in Idaho that they would truck it to.
So you guys assume that you're getting the potato peel waste for free, right? So do you think that's realistic when you're making, I think it's $51 million a year? Just like not from a use standpoint, from like a business standpoint, your entire process relies on these people giving you this stuff for free, so they might want a portion of that, like a small percentage or something.
So a couple notes on that. First of all, since it's a waste, they have to pay to get it disposed of, and so we'll be taking it that they wouldn't have to pay at all for the disposal. But we actually took into account also the transportation, which is not really done. Like a lot of times they would transport it to you. Like So like waste products that are used for something else, they transport that waste for free to the plant. So we actually took into account transporting, like getting the waste from their plants to us, which is like kind of like our safety, I guess, right there. So we would be additionally helping them, so we're only benefiting.
Kind of going off of that, you guys said with the production of potato waste, you went globally. Do you know how much would be in Idaho, and kind of going off what Mason was saying? Would that be a concern if you were starting to take away what some people might rely on to use for their livestock?
Yeah, so I can't remember off the top of my head the numbers, but the U.S. is, I believe, the largest producer of potatoes, and Idaho is the biggest producer of potatoes in the U.S. And around Eagle, Idaho, there's a few potato processing plants around, very large ones. I couldn't find exact numbers, but it should be in the millions of metric tons of potato peel waste, so more than enough for our current process.
And I mean, going off that, like, answering the second part of your question.
No.
Oh, sorry. Yeah, just continuing off what you asked before. It's not like no one's disposing of this. Like, there's companies right now that are still paying to dispose of this, and obviously a lot of it is going towards like, a portion of it is going towards like feed and fertilizer. As to say, like, we don't really know exactly that number, but what we're saying is we're helping a lot of these companies out that paying for this disposal, and like figuring out that number exactly. We'll have to do further research.
Most bulk processing or commodity processing plants are sited closest to the source of the raw material. I'm surprised that your analysis came out that it was less expensive to ship the potato peels down to Texas than to ship the
So actually that might have been a misclarification there. So our processing facility is in Eagle, Idaho. So essentially what that whole transportation thing is, the resin production is in Eagle, Idaho, and then it'll be put into hopper cars and then shipped down to Dallas, Texas, and that's where the plasticizers and the thermoformers are. So that might have been my mistake in like laying it out properly for you, but our production facility is right where the raw material is, so that heaviest part of that raw material, the potato peel waste, goes, it's very short distance of trucking to our facility, making the resin, and just loading it into hopper carts, and we're like right on the side of the railroad track, so it's...
They're keeping the water in Idaho. Good idea. Although they could use that water in Texas once in a while.
Well, no, thank
Yeah.
you.
Thank you guys.